Thank you for clicking on this video and welcome back to our ipXchange subscribers. Stay a while and learn how to design a custom battery management circuit for any chemistry, to learn about a new type of battery with some wild advantages, and to see me rush to design a product in under a month for the Earth's largest electronics trade show, CES. The product that I'll be designing is an improvement on restaurant pager systems. You know those buzzing rectangular pages that you get when you get food from food trucks? It turns out they've got a really bad flaw, and it's to do with the lithium polymer battery that powers them. Despite having loads of capacity, they can't charge fast enough. And on busy days in the restaurant, that means that eventually your pager goes dead and somebody doesn't get their food. How do I know this? It's me. I didn't get my food. What I had to do was immediately and abundantly clear. Fix the restaurant pager. One more thing, I only have 3 weeks to do it before I fly out to CES. So let's get started. This video is sponsored by Nichicon and their range of lithium titanate oxide batteries, or an LTO, and it's the battery that we'll be using to power this project. This one specifically is the SLB04255L040 from Nichicon. There are many reasons that you might want to use an LTO. So let's talk about the data sheet here. It says, it's got some good ones here, excellent cycle characteristics. It can be charged, discharged multiple times. This means it's gonna have a long life. Possible to use in cold regions, down to -30. You're not going to find that with most batteries. Extremely low possibility of rupture and ignition. Now, these batteries are incredibly stable, and I think we're gonna cut one later for you as well, just to prove that a bit more. But I think its most useful characteristic is its characteristic as being a middle ground between a battery and a supercapacitor. Let me explain. Batteries have a nice stable output voltage as they are discharged. For a battery like this, that may look something like this, from 0% up to 100%, mainly a flat curve, and that's very helpful to work with when you're powering your electronics. A supercapacitor is a lot different. At 0% to 100%, we see this exponential decay function. It looks something like that. Where capacitors have batteries beat, however, is in being able to put more energy into this faster. You can cram energy into this faster than you could this battery. The lithium titanate oxide cell is a middle ground between these two. It's the ability to have a nice flat state of charge curve, like this one for our battery, whilst being able to cram energy into it extremely quickly. Back to this. Why didn't I get my food when using a LiPo-based pager? It's because over the course of a busy day, the pager will start charged, right? Then it gets discharged when it's used, it gets returned, and in the time between me and the next customer, it doesn't have the chance to charge completely, right? And then it gets used again, and again, and again, and again, until suddenly, it's out of charge. The fix for this is simple. We need a bigger battery. Well, look, not quite. A bigger battery is more expensive and also a bad engineering decision. Instead of turning to a larger cell, we could turn to a battery chemistry that could charge faster. Because remember, that's our issue. Our cycle would begin to look more like this, depleting after every deployment, but fully charging in a fraction of the time. Right now, excitingly, we're experimenting with a lesser known metric of battery performance, the so-called C rating. A C rating is a battery's charge current over its capacity. For a lithium polymer pouch like this, its C rating may look like this. A charge current of 250 milliamps over a capacity of 550 milliamp hours. That will give us the C rating of approximately 0.5. Something interesting that you may have already noticed is a C rating will tell us how long it takes a battery to be charged. A C rating of 0.5 will equal 2 hours to be charged from completely empty to completely full. Let me show you why the LTO batteries are cool now. This Nichicon LTO cell only has a capacity of 4 milliamp hours. Don't laugh, all right? 4 milliamp hours. This is why it's cool. It can charge at 80 milliamps. That means, with our equation, we get 80 over 4, which equals 20. 20C is how fast this battery can charge. That is very, very impressive. Once again, last time, we can get how long this will take us to charge by taking 1 over the C rating. 1 over the C rating in this case is 1 over 20. To get that in minutes, we'll multiply by 60. That's going to give us 3 minutes. Now that we understand why I'm choosing this kind of battery to redesign the restaurant pager, let's get designing. For this system, we need 2 parts. We need a transmitter, usually controlled by restaurant staff, right? Your food is ready, I flick a switch. And we need a pager, which is given to the guests. The transmitter unit needs to send out a wireless signal to the pagers that tells a specific pager to buzz. I'm gonna use Bluetooth to do that. For the pager unit, we need a Bluetooth microcontroller to scan and intercept these transmissions. When it does determine it's being called, it needs to put out as much light and make as much noise and give as much haptic feedback as physically possible so that you know your food is ready. To do this, I'm using a buzzer, LEDs, and a small ERM vibration motor. We're aiming for around 60 minutes of battery life in the field, with 30 seconds of a high power buzzing event after this. So I chose this Shoal ESP32-C3 because of its extremely low sleep current and Arduino support. All of this functionality will be powered by this Nichicon LTO cell. So we'll need to make some circuitry to manage the cell's charging and discharging. Let's talk more about that and how to use this new technology. But we better be fast because I only have 13 days left. To use a battery, you must give and take energy responsibly. If you don't, some will go bang. If you are using a common battery chemistry, like lithium-ion or lithium polymer, you can choose from thousands of dedicated ICs to manage charging and discharging and protection for you. Such an IC is the popular Texas Instruments BQ2970 lithium-ion battery protection IC. It can detect charge over current, discharge over current, over voltage, and over discharge events. If it detects one of these, it can electrically disconnect the battery to keep it within safe operating conditions. Lithium-ion cells have lithium-ion BMICs. LiPos, LiPo BMICs. Lithium titanate, they're a little bit rarer, and no semiconductor company actually produces one yet. Treat you right, we're going to have to make a custom one. But next time, you can just copy mine. This design has been made to charge our LTO cell. So this part here will charge it at a specific current and a specific voltage. And this section will protect it if it so happens to go under an undervoltage threshold. So we got charging and a UVLO. We'll go over those soon. But if you want to use this circuit for anything, you're more than welcome to. There'll be design files in the description of this YouTube video. You can essentially change a few values and this will work for any circuit. If you're working with something like a bit more spicy, lithium-ion, you might want to include an overvoltage threshold and output current managing as well, but that's up to you. A wise man once said, "To charge a battery is to understand it." If we search the datasheet of this particular cell that we are using, the SLB, I won't say the whole name. Regardless, you'll find this, a charge characteristic graph. Now, using my tweezers as pointers, this red line, 20C, is a line that we're going to be following. So it's saying that as we charge up, our capacity is nothing and we're going to see a rise in voltage, and then here we keep a constant voltage and we finish the charging. Essentially what we've got is 2 sections. We have got constant current and constant voltage. Essentially what we're going to be doing is we'll be charging at a constant current, 18 milliamps. And as we charge up, we'll have a variable voltage. And then once we get to this point, we're going to be holding 2.8 volts. And our current will do something like this. Taper off as our battery finishes charging. I need an IC that will provide regulated current until it reaches our charge voltage. And when it does reach it, to just hold it. After hours, and I mean hours of searching, I came across the most unlikely candidate. It was a supercapacitor charger by Texas Instruments called the BQ25173. Though we are not charging supercapacitors, this IC is perfect. These resistors, they control the charge voltage, and this resistor controls the charge current. Great. Now that we can charge the battery, we need to ensure that it is not discharged beyond a limit. That limit can be found on our state of charge curve, or SOC, showing that they are empty when they reach 2.2 volts. LTO batteries are safe by design. You can stomp on them. In fact, I'm going to cut one in half to prove that to you right now. I think the first thing to do to make sure it's a fair test is to charge it. 2.8 volts. Okay, battery is connected. So you can see we're currently in a constant current mode, and our voltage will start to creep up over the next minute to 2.8 volts, at which point this current will start decreasing. My tool of choice for today are my pliers. Look at that. Can't even feel heat. It felt like a little bit of a waste, but it is nice to see that it doesn't go bang. The battery protection circuit starts with a voltage reference using this Zener diode, and also an op-amp buffer powered from the battery. So these are powered from the battery, and they're creating a reference of the battery through this voltage divider here. Now, let me know if you know why I had to use a voltage divider there. Tell me in the comments. Now, at this node, we have a reference of our battery voltage from our battery over here. We have a reference of it that is roughly 80% of it. Let us skip this block here and come back to it, and we'll talk about what these MOSFETs are doing over here. So, out of this mystery section behind here, which you might already know what it is, if we see a high signal come out of this block before, what we're going to see is this N-channel MOSFET turn on and pull this P-channel MOSFET's gate to ground. That is going to open up this section as a short, and the battery, which sits on this node, is going to be able to discharge into the rest of the circuit. Essentially, if this node here is high, the battery will flow, and if it's low, the battery won't flow. So, this part, 1.8 volt reference. This part is providing a reference of the battery voltage. This part cuts the battery off if this node here is low. You may have predicted what this is already. This is an op-amp hysteresis circuit. Its job is to produce a high signal if it sees that the battery has charged to 2.8 volts, and to keep it high until it discharges to 2.2 volts. Once it reaches 2.2 volts, it should keep this node completely low until it's charged back up to 2.8 volts. Essentially what this is it's a way to protect the battery's longevity. This circuit is fantastic, and you can make it work for your battery chemistry too. Essentially all you're changing around is R17, R15, and whatever this reference voltage is here for you. Let's take a quick look at the rest of our circuit. So we've got a boost converter that will be turning our battery voltage anywhere between 2.2 and 2.8 volts into a 3.3 volt source for the rest of the circuit, which includes a Bluetooth microcontroller, this Xiao ESP32-C3. This will be taking care of all of the Bluetooth communication, but also the alarm circuitry, which is down here. We've got a buzzer, piezoelectric buzzer. We've got an ERM motor, which will be producing the vibration, and we also have a few different LEDs. Up to this point, we've only been talking about the pager unit, the part that's given to you in the restaurant. But let's talk about the part that the chefs will use. This is the transmitter unit. It has a few jobs. One of its jobs is to charge the pager units as they come in. So there'll be two USB ports, and you can plug the pagers into the USB ports. It also has switches. This determines when a pager is going to be called. And these are LEDs just to show you that you're calling a pager or you're not calling a pager. Once again, ESP32, same microcontroller using all the same libraries. This section down here is controlling a display. It's actually this exact one here, the DF Robot 4 7-segment display. That's going to show the percentage of batteries. So we'll have unit 1 here from 0 to 99, unit 1 here, 0 to 99. Good little section there, needs a level shifter, don't worry about it. And the power supply. We don't really care about that. It is time to get designing the PCBs. At this point, I'm about 1.5 weeks away from CES. Pressure is on because Nichicon is counting on me to deliver this LTO cell demo to their showcase on their booth. As of recording this, I have about 12 days left until I catch my flight. If I get this PCB done today, I'll send it off to PCBWay to be fabricated. It could still take 10 days to get back to me. If that happens, at that point, I'm only gonna have 2 days to construct the full system. soldering, writing the firmware, making the enclosures, plugging in everything and testing it. I'm running out of time. Nine days after we've last spoke, I sent these PCBs off and they've just arrived. Now, they're looking pretty goddamn good if you ask me. I got them in blue because that's sort of Nichikon's color and I'm happy to go by their rules there. You can see this is where our battery will go, just like that. This is an ERM buzzer, LED. Here's where the ESP32 goes. It's all looking quite good, really. There you go. If lost, return me to Nichikon, the ipXchange logo. These look fantastic, but I've got 3 days to go. And if I'm ever going to make this deadline, I'm gonna start now. Let's get building. I start by tipping out the exact amount of components I need to build the pages. Next, I apply solder paste to the PCBs and I place the components carefully. It's time for my secret weapon, the hot plate. Instead of manually soldering each component, I can solder every single one at once by applying heat beneath the board. The recordings from this process, whew, mesmerizing. Now that I've soldered all of the surface mount components, I'll hand solder everything that's left. This is the completed pager. Whilst you and I, the electronics engineers, might appreciate a naked PCB, the general public at CES cannot and will not be trusted. I'm going to fabricate an enclosure for them and also the transmitter units, which look like this and are absolutely massive. Let's do it. After connecting up all of the wires, it was time to write code. At this point, all is complete. So I put hot glue everywhere to secure those cables to transit, and we seal them up. Welcome to CES 2026. This is the show that I'm building this for. As I've said, it features a Nichicon LTO battery inside, and this is a restaurant pager system. So I did make it in time, but it was a hell of a rush. Let me show you how this actually works. This is a restaurant pager. Get a little bit closer over here. This is what the end system will look like, and this is the baseboard that it connects to. In itself, this is connected over Bluetooth, and when I flick this switch, it will start to buzz in about 5 seconds. It'll check it every 5 seconds. You ready? It's vibrating in my hand and you can hear it. There's LEDs just like a normal pager should work. Now, I've just come back to the restaurant. It's time to put this away and now it starts to charge. See that? We're charging up. That is how quick that these batteries charge from what looked like 60% all the way up to 99% again. All right, it's all said and done. We're here at CES and the demo has been a success. What do you reckon?
Well, it's a blast. So we have had so many people here at the booth of Nichicon at CES, and yeah, this is a great product you made ready on time finally.
Oh, yeah. Honestly, I couldn't believe that I made it in time. It's been like 3 weeks since we talked about starting this.
Right.
When do you actually need these done by?
Well, there's CES in Las Vegas in 3 weeks. How about that?
What? 3 weeks?
Yeah. I'm serious.
This is only one application of these batteries. However, we're showing how fast it can charge and discharge. Yeah. What are other people doing with this?
Well, we keep telling people that come by the booth to explain what these batteries can be used for. So these batteries can be used for that purpose, but another 2 purposes that are interesting. That is energy harvesting. Mm-hmm. So you hook up the battery together with some kind of an energy harvesting source, like a PV cell. Mm-hmm. That is one option. Because then you don't need a very large capacitance. You can refill it all the time.
Yes.
And this battery is extremely current powerful. So when you need pulse current, it's there for you.
Yeah.
And if you refill it, you don't need very large capacitance. So you can have a small battery. So that's one other. And the third one of interest, that is what we hear from many people here at the show, that is they have battery powered products, but they want to extend the lifetime of them. So they are maybe today at 5 or 6 years, dependent on the usage, and they would like to come to 10 years. So we are telling them, continue using that primary battery that you have, but take the energy over from that primary over to our small cell, and then let this small cell do all the hard work. That will...
The high pulse currents in transmission events.
Yeah.
Right. Okay.
It releases then the primary cell from that bad job that will reduce its lifetime.
Yes.
And by that, substantially, you would extend the lifetime, actually. And not only extending the lifetime, you can also make sure that you have performance outdoor in all temperature climates. So many batteries have difficulties to operate at very low temperatures. But these batteries, they work, fully operative at -30. Charge and discharge.
That's totally different from batteries. Awesome. All right, back to you in the studio. Ladies and gentlemen, that is how I developed a custom product to fix an existing problem in under 3 weeks for the largest electronics show on the earth. I want to leave you with some design inspiration because I think it's highly probable that you will make a great product with these Nichicon lithium titanate oxide cells. LTO cells have 3 main use cases. One of them is charging and discharging rapidly, and that's a characteristic that we used for this design in this video. Another is quite the opposite. You can use them for micro energy harvesting. Indoor light, photovoltaic cells, heat from Peltier devices, vibrations, anything that produces only a tiny amount of energy, these small cells will happily harvest it. The final use is for supplementing a primary cell. For example, if you are powering some IoT device from a non-rechargeable primary cell like a coin battery, and you have energy-intensive events like a transmission to a satellite, this can and will damage the coin cell and reduce its life significantly. If you include an LTO cell, even smaller than this, in parallel with that primary battery, it's an inexpensive way to extend your battery life by years, because this will take the brunt of that high energy hit. All schematics, all PCB files, all firmware that I developed is available completely for free use. Please use it. You can download the resources from the link in this video's description, which will take you to ipXchange.tech to request them. After that, they're all yours, sent to you instantly. I'd like to give a great thank you for Nichicon for sponsoring this video. We here at ipXchange cannot wait to see what you make with an LTO cell just like this one.